So I would like to discuss a few things about, with more visuals possible. I would like to discuss a little bit more about real-time aspects of synchronization. Can we implement these things in a way that your real-time systems will be able to guarantee things, or is that independent of that? You need to worry how your synchronization mechanisms are being implemented. Is that clear to you how they're being implemented? What synchronization mechanisms would you use from a real-time perspective? You are aware you do need to use synchronization mechanisms every once in a while. It's not only your scheduler, you also have to communicate between tasks or between resources in more general terms. Does this have any real-time implications? If so, what? Let me ask more specifically. Okay, this was about monitors, where we ended last time, and we said that monitors were still leaving something to be desired. Hence, we are actually not using monitors today anymore, but we are combining those things. And one of the reasons why we are actually using those kind of setups is their real-time predictability, their ability to implement is highly efficient and completely predictable. You see that these things are efficient and predictable, or is it just a gigantic piece of sugar coating over something more simplistic and more predictable? You have a specific number of queues defined on the whole thing, and we need to talk about the evaluation mechanisms for those queues. This is just what all you know, readers-writers problem, defining read-only operations, and you can allow many read-only operations on the same data object, while only you can allow one write object at the same time. Preaching to the choir here, right? That's all easy and straightforward. Slow me down if anything is not completely obvious for you here. So you do have that readers-writers problem solved. Everything turns into constants if you use functions. This is all easy, and then you can formulate something like this in a completely easy and straightforward way, and also in a very safe way. You saw all that. We don't have to do that. But the more interesting part, if you look at something like this here, for example, at what point in time are these predicates being evaluated? You have predicates defined here. When number is larger than 0, when number is smaller than buffer size. When are these predicates being evaluated?
Every time you write.
Every time I write, wrong.
Every time another task, well, first of all, when you first call it, and then it's false every time another task finishes a procedure or an entry.
Yes, so every time you leave a protected object, not when you write on the data. Because why are you not re-evaluating the predicates when you write on this number variable here? Why are you not re-evaluating the predicates then?
Because you wouldn't enter the object at that point. Like, it could change for you as the object. It
could change again. Right? You could be in the middle of a procedure changing number 5 times in a row. There's no point re-evaluating all of your guards at this point, because there's no way how anybody else can ever enter at this point. So you're only re-evaluating when you leave a procedure or an entry. Not when you leave a function, because functions are side effect free here in that context. So they couldn't have changed anyway, so you don't have to even look. But you need to re-evaluate when you leave those. Now that's actually a very small number of re-evaluations which you have there. And they're happening at very precisely defined times in your code. Ada does give you another alternative, but both are equally predictable. The First one is actually the one which is commonly implemented, which you also have in your system. Exactly what you described. Whenever you leave a protected object and a function, an entry, then you reevaluate that one. But now let me ask a bit deeper, a bit more. Example, who is evaluating that? The task at the front of the entry queue? No. The task which is leaving. Why? There's no task switch. Right? The task which is leaving is currently running anyway, and you just piggyback this little job. This is part of you leaving a protected object. When you leave a protected object, you have to reevaluate these guards. No context switch required. If I do it the other way around, if I say the front task has to reevaluate, the front task may reevaluate only to put itself back to sleep because maybe they're still closed. Okay, let's go further. If you look at this example here, first, can you convince yourself that there is no way how tasks can actually circle through an open predicate, an open entry gate? Can you convince yourself of that fact? Or are you worried that once this thing here is open, releases open up, then a few tasks are slipping out of this protected object, and they're immediately racing back into this protected object, and immediately trying to get through this blocker straight away again? Wouldn't these tasks be able to keep this blocker open infinitely just by leaving this blocker and coming back straight away, squeezing in, leaving it, coming back straight away again? I know you know it. Just slow down for a moment. I want everybody to have a bit of a think what is actually happening here.
There's a queue, right? So when the task leaves, it's put back of the queue. And the other task.
Yes. No, it's not overtaking the other tasks. That's not the problem which I meant. The problem which I mean is you want to have exactly 5 tasks here blocking, and then you want to release all 5 of them, or you want to actually block 5 and the 6th one is kicking them all off, and then you want to release all of them, and then you want to close after that. Is it possible that these tasks are just racing around and keeping this guard open infinitely? They're not violating order. They're still getting to a queue, but could they actually just keep it open? Okay. Okay. So you two remember that there are multiple queues here at game. It's not a single queue. And there's a queue which is associated with the protected object as a whole, and there's a queue for each individual entry. And we need to have, again for predictability reasons, we need to have an internal progress first rule, which makes sure that the internal entries will be evaluated first. So all of these guys which have been queuing up at the entry proceed queue, they will be evaluated one by one. And only if you're running empty with the internal queue will you ever consider the outside queue and any task which comes from which is coming from the outside. And that means you're clearing that out. You're reducing that to 0, closing that entry, and only then the tasks which have been racing around, possibly, will be reconsidered. Yeah.
What is proceed check count evaluated? Because like if you just evaluate that when you leave an entry, that how does that work?
Count is evaluated exactly at the same time when all the other predicates are evaluated. It's not evaluated while you're running in any way inside of these entries. It's only evaluated when you leave this entry.
But no one's going to get into that entry until that evaluated is true, right?
Yeah.
So no one's going to leave the entry for it to be evaluated.
Okay. No, I see what you mean. you're also evaluating them if you cannot make any kind of internal progress. So this is the initial evaluation when tasks are coming from the outside. Yeah. Otherwise, you're right, you would never be able to open that ever. Okay. Okay, so far so obvious. Okay, now comes the interesting part. If you want to make this all really performant, and you have 5 tasks queuing up here, can you do without a task switch? Like any task switch? You have 5 tasks who all want to go in there, right? Do you actually need to activate those 5 tasks? Think about this for a moment. Is there another way? You're the compiler designers now. This is advanced class. This is not second year. We're building the whole thing. Would you build this compiler so that the compiler is actually switching contexts 5 times? Just for evaluating this release, is proceed count larger than 0 in 5 different tasks? Would you do that? Why? Is what? No, it doesn't. Doesn't.
It can be like the project object and always one task, always running on behalf of all the other tasks calling the project object, and only hand out the result to the task.
That's dangerous, what you're suggesting now. Now you're suggesting that you have an additional task which nobody knows about, which does it somewhat secretly. That's dangerous. You're actually now making an active entity out of a protected object. Other idea?
Well, I was going to say, you don't really want to pick the first one.
The first one which actually has been released, which goes out of that one.
Because it could potentially be held up doing the work of all the other ones. So
Yeah.
ideally the last one in the queue could potentially do all the work.
The last one in the queue. Okay, so you change over to the last one in the queue? Yeah?
So you could let the first one in, and because that operation, like, it doesn't really depend on anything other than like the internal state of the object, like
Yeah.
the queue.
Yeah.
If you get it to do the operation, then just dequeue a task from the queue, and then start reading the operation.
In the same task.
Yeah, without actually switching tasks, just dequeue.
Yeah. Yeah. So you would actually take the first task, which is leaving, and keeping this first task just spinning here around, and basically doing nothing then releasing all the other tasks, but doing all the coding, doing all the statements inside the same task. Okay, first, would that logically be correct? You don't think so?
In this case, I think it would be, because like that operation doesn't depend at all on what task is doing.
Okay. Why do you think it's dangerous?
Because the second task will be released before the first task is, because the first task is still doing all the work.
Yes.
And it's in a queue, and so the first task should be released first.
No, but after they have been released from the protected object, there is no queuing and order guarantee promised to you, right? You just know that after they go through that one, they will all be freely running again. There's no queue at the outside, at the end point of the whole thing. Now, the first, you're worried about fairness, but my first question is about logical correctness. Am I violating logical correctness by doing that, by keeping one task doing actually all the work? Would that one task have access to the data? Yes. This one task, by definition, has the same access to this data like all the other tasks applying for this protected object. Because you're only manipulating data inside a protected object here. So logically, this task is not doing anything different. This task is manipulating data in a shared area to which all other tasks would have access as well. So the outcome, the logical outcome, is exactly the same. You're still worried about the fairness of the whole thing, that one task is doing all the hard work here, and the other tasks are being set to ready.
But isn't it quite similar to making projected object
An active task?
activated? Physically, instead of creating
No, this is more efficient. Because if you make a protected object an active task, you have at least one more task switch. You need to switch to this active protected object task.
What if the first task that ends up doing all the work really needs to get out of the critical section and do something else, like something really important?
Yeah, like what if it's in an important statement or whatever? And maybe it'll get kicked out at some point.
Yeah.
And maybe the operation takes about 5 seconds, and to do it 5
Yeah.
times takes 25 seconds.
Yeah. Yeah.
Yeah.
Okay, so now here comes the scheduler to play. Whether the scheduler has enough knowledge to make that decision or not. Because that may be the case, may not be the case. If the scheduler knows that all of these tasks are on the same priority level, have all the same deadline constraints at the moment anyway, then it may be perfectly fine to do it like that. And I can still release the task in the same order. Assume I have only, say, one CPU available. That means the other tasks are not running. The only thing I have changed is I killed the context switches out of my code. This is the only thing I've changed. So I have not changed any order, but this is only true on a single CPU machine. If I have more than one CPU, this is a more complicated question. In a symmetrical multi-processing environment, that need to be considered a little bit more carefully. Still, avoiding context switches increases predictability and timing precision. Context switches are intrinsically dodgy when it comes to predicting them precisely. Depending on the underlying system, it's a beautiful real-time operating system, maybe okay. In general, it's a bit questionable, so try to avoid it when you can. Right? But it's a kind of a surprising insight. You have 6 tasks here running, virtually, from the perspective of the programmer. But there's no need to have 6 tasks running, because they're running under mutual exclusion anyway. There will only be one task running at any given time. How about I just do this with one without any context switch? This is actually exactly what happens in your Linux environment. If you run that kind of environment on top of Linux, this is exactly what happens there. And that's done for a number of different reasons, not only for efficiency, but also for the fact that it is almost impossible to hand over an open resource, an unlocked resource, from one process to another one. They would need to have additional overhead to actually lock it down, hand it over to somebody else, and then open it up on the other side again. There's the implementation issues with the POSIX interface, which bites you on the Linux implementation. So, interesting to looking at it from a conceptual, concurrent programming perspective, and then looking at it from a execution, real-time, performance, predictability perspective, and the code can look very, very different, which actually runs without violating any promises which we have given to the programmer.
Would it, like the task outside calling this project object need to pass in some time?
What if the task outside has to do what?
To pass in some their local memory.
Pass in some data, local memory. It depends whether this task has the same access.
But first, by definition, has the access to only itself, like the local variable in itself.
Yes, that's correct. But it has to be able to provide a reference to this data. If you have an access type to some data structure from outside, this is probably a killing point. If it's a value which is already on the stack anyway, because you hand it over as a parameter to this protected object, then that's not an issue, because it already has been copied on the stack anyway. The question is, do you have access to that other stack so directly? And it depends very much on the compiler implementation whether this is possible and allowed or not. But you're right. This is something you have to very carefully consider. Okay. Cool. Goes for all of that as well. Entry families, you probably haven't used them in a while. Requeue facility. We addressed that last time. Requeue facility is the common answer to nested monitor calls, resolving them, because you can just requeue to another protected object instead of using another entry call. And A, you're not getting any nasty compiler errors or warnings, and B, you're releasing the logs behind you if you use a requeue facility. Those are just classical examples of entry families and requeue operations. Again, plenty of requeue stuff. Now, this is important and essential for you guys on the real-time side. What can you do from within a protected object? And here it is, some of these things are producing warnings. On your Ravenscar profile, they will definitely produce errors. Basically, everything which is potentially blocking is not allowed inside a protected object. So you're not even allowed to attempt nested protected object call inside a real-time system. There has to be all non-blocking operations in there. That means you can't predict how long you spend in your protected object. And that combined with the fact that we have to manage the priorities of all the tasks which are coming into this protected object in a clever way for the scheduling chapter, which is the next thing which is coming at you, will enable you to do this in a very predictable real-time way. Yeah.
Can you not separately work out how much time the guarantee on how much time the engineer trying to make a protected object to another protected object will take, and then you can back that in and do the analysis like another thing?
Yeah, but if all protected objects can call on other protected objects, you already lost. Because how do you detect circular calls here?
But there's lots of things where you can break it if you really want to.
Not if you don't have any possibility to put a non-blocking statement in there.
You can still.
Sure, you still have to solve the holding problem to make sure that there's not an infinite while loop in there, if that's what you mean.
I mean more.
But that's the only thing left. So unless I have actually an infinite recursion or an infinite while loop inside my code here, I'm pretty safe. To open the door into potentially blocking operations is a much more complicated story, which I have to look at. Because if I call another protected object, which can be potentially blocking, how do you predict this blocking time?
I thought you did that analysis of your system anyway. If you could be potentially blocking forever, doesn't that make your whole system possibly stall?
No, that's true. But first of all, if I allow to call another protected object, you would need to make sure that there is no circular dependency in the system, that all protected objects are coming back to the first one, which is still locked down, which is definitely infinite blocking operation, which means you need to have an automatic deadlock detection mechanism for that specific case, which is hard to do.
Is that hard to do?
Yeah, it's hard to do.
Is noise data considered as blocking?
Yes. In the Ravenscar profile it is, yeah. Because the wait statement or the delay statement has a parameter. And this parameter can be anything. It can be the parameter wait forever. If it would be guaranteed to be a constant, you can argue this is just like a statement sequence. This is probably what you're thinking at the moment. But this is not what a delay statement looks like. A delay statement can be parameterized with anything.
But like for the integer in data, it has a maximum value.
Yeah, but a pretty big maximum value. And considering that all time variables have to be able to spend at least 50 years, I think that's a pretty large number. All right. So that's looking at different shared memory-based synchronization mechanisms. You have seen that diagram before, I think. Just putting up the hierarchy of things which we have here. POSIX gives you puzzle pieces, but nothing hangs together really. You have separately semaphores, condition variables, and synchronization methods, which all are scattered over your code. You have the power for all of these mechanisms, but there is no scoping anywhere for obvious reasons, because the programming name is a library call, like collection of library calls. Java has basically synchronized methods and the notification system someplace, and everything else is libraries built on top of that. So it depends on how many libraries you want to call part of the language and whether you want to mix language primitives with libraries. Usually wouldn't do that, but just your choice whether you want to consider library calls here as part of the standard library in Java. It's still nothing that the compiler would be aware of. The compiler, even if it's a standard library, the compiler still doesn't give you any error messages for that. Visual C++, Visual Basic, you do have data structure encapsulation, and I would say almost monitors. It's a pretty close call to a monitor, so I would be happy if you include monitors here as well. It's a bit debatable whether it's a clean, full-fledged monitor in those languages. C++ 14 or C++ in general is a bit of a moving target, and there is more and more scoping and locks on scopes embedding itself into C++. I can only invite you to explore more on the current state of C++ here. Who has been working in C++ for concurrent systems so far? One. Okay. What have you done in C++?
None of those, just some networking, and I used semaphores.
Okay. So this was just then classical C++. It was not C++ 14. Okay. Speaker? Now C++ is way further than that by now. Okay. I can only invite you keep yourself up to date with that current development. It's not yet on a development stage that we are embedding this into concurrent programming at the ANU at the moment, but it's could welcome. There could be a bunch of other languages overtaking it on the along the way. Rust is a mixed bag of all kinds of things, and you can also say Rust doesn't have any of that. Depends on your perspective. The original Rust language design had all of these things as part of the actual language, and then they got cold feet and pushed all of that stuff into libraries and removed it from the language. I think that was one of the worst decisions they have made, if you ask my opinion on that. But this was tend to go for more simplicity in the language and more cleanness in the language itself. But for the price of abandoning most of concurrent programming features into library. I also couldn't quite agree on the concurrent features which I actually wanted in the language, and then the usual diplomatic compromise in an open language is let's not nail anything down, let's leave it open to 5 different libraries you can import, and then you have all possibilities open. Yeah, maybe. Okay. Languages which have clean monitors in them are pretty much extinct by now. And in Ada you have pretty high-level concepts, and you also have test and set level semaphores on the lower level. at the same time. High-performance computing synchronization, we don't really have to concern us with that in this course, because this is all pretty far from real-time systems, as amazing and interesting it is. Okay, message-based synchronization. What's the difference between message-based synchronization and memory-based synchronization, in a few words? Why is it different? Both of the entities have to be active, then it's message passing. Right? Memory-based has, as one of the communication partners, passive memory, just lying there, and you synchronize onto those passive entities. But message passing means you have active entities in the whole thing. Which of your languages does have message passing? Do you know any languages which have message passing? You can do it in C with a library. Between what active entities? We just defined message passing is, by its very core and definition, a communication method between active tasks and processes. Yeah. Now, a programming language which doesn't even have the concept of processes is a little bit in trouble.
So the definition of active?
Definition of active means that you have a concurrently independent thread, process, task, whatever you want to call it. So you have something which is logically concurrently running. And you have concurrent entities which are communicating. Those concurrent entities are considered active in this context here of message passing. Does it answer the question? Okay, that means programming languages which don't have the concept of concurrency don't have much of a chance to implement anything in terms of message passing. But hang on, isn't there this MPI thing and OpenMP, and isn't that message passing? How is that message passing? Who have heard of OpenMP and MPI and these things? Okay, is that message passing? It says so. It's called message passing, right? But it's also a C library. Right? What qualifies this for message passing? Those library calls only make sense if you actually have processes or different computer nodes in your system to start with. As a communication system between your different functions and procedures in your main routine of your C task, it's a completely pointless operation. It's not meant for that, it's not used for that. It's actually used to make communication channels available between computing nodes. So the whole computer becomes the active entity in that context, or at least multiple processes which have been running different programs and then use these library interfaces to send messages to another active process somewhere. A lot of that is in your head. The compiler has no idea about this. So you need to rely on a whole mixture of operating system, network interfaces, and your library calls to make this a reality. Any other languages which offer message passing? Never used message passing?
I used Go, but I think it has something like channels.
Yeah, that qualifies, yeah. Go certainly has message passing, yeah. Java does explicitly not have message passing.
Comes with a nice concurrent key.
Say again?
Comes with a nice concurrent key.
But can you actually exchange messages between tasks in Java? There's no interface for that. There's no language feature for that. You can leave in some hidden mailbox some information. You can synchronize some methods and you leave it in those synchronized methods for somebody else to pick up later. But that's memory-based synchronization. This has nothing to do with message passing. So no, they forgot that. There is no feature like that. Nobody played with Erlang? classical programming language which is based on message passing and nothing else. So these languages don't offer any memory-based synchronization at all, only message passing. Is message passing, compared to memory-based organization, is this more efficient or less efficient? Depends whether you have one core or many. Okay, if you have multiple cores.
You don't need to do tasks which just keep them running. If you only have one CPU, then you do a lot of comments, which you would better to use one just for the
Okay. With message passing, you have a few less possible. Yeah. Oh no. Sorry, you were just waving. You have a few less possibilities to optimize here. But message passing has a few other benefits.
With message passing, you have to wait for the person who's sending it to really accept it.
At least if you have synchronous message passing. Yeah.
Okay.
You also have asynchronous message passing. Yeah. That has different problems to it, but yeah, you can also have asynchronous message passing. Usually, when you pass messages over the internet, you're not actually hard synchronizing with your task on the other side. You're synchronizing on a very high protocol level, but not on a low protocol level. There it's asynchronous. It becomes synchronous if you go up in the TCP/IP stack at some point. So classically, you move up to UDP, it's still all asynchronous, and beyond that, it becomes a synchronous protocol. In terms of predictability, does that make a difference? In terms of, in terms of integrity, in terms of safety. If you have to verify your programs, would you prefer message passing or memory-based synchronization? Memory-based. Why? Yeah, okay. This is one argument, yeah. Why would some people say that message passing is actually a safer option? Certainly the airline people will tell you that because they explicitly banned memory-based synchronization.
Will they be completely separate with shared memory? You have to, if you did it wrong, you could start getting lots of errors that would be very difficult to track. Whereas with memory-based, with message passing, they're two completely separate entities with their own memory and everything like that, and you just send a message across, and it'd be really, I would find that easy to verify because there's just one thing going across, you don't have to worry about all of it.
It's an interesting point, yeah.
Which shared memory is that volatile memory?
Shared memory is volatile from a logical perspective, so that makes it harder to verify because you always have to consider that something is going to change there. Yeah. So whenever I can declare any piece of data a constant, your verification process will become easier. So far you follow, right? Now if I have message passing, every piece of data which I pass over to another task is by definition a constant, which I hand over to somebody else. They can work with that constant, never has to write on that, never has to do anything with that, and that's done. And you hand something back, it again becomes a constant which comes back. And only at those points do I have to verify and check up on this data. Now, in shared memory, I have to make sure that the whole shared memory area is consistent in terms of data structure. It can change. It's by definition mutable, all the data which are stored there. So you have to handle mutable data because that's the definition of shared memory-based synchronization. While in message passing, I can logically fall back on the principle of everything are constant parameters which I just hand over. So you can move into a world which is much more pure functional programming. But everything which I'm handing over becomes, I'm only dealing with constants all the way through my system if I'm only basing everything on message passing as opposed to shared memory-based systems. So that's one way of looking at it where you go, Message parsing may be cleaner if you want to verify that. But on the other hand, you need to synchronize multiple entities there. So from a timing perspective, it may be more complicated again, and have possibly more possibilities to deadlock things. Maybe. Okay. So I don't need to bore you with any of that. You know what synchronous message parsing is. You know what asynchronous message parsing is. Can you emulate asynchronous message parsing by means of synchronous message parsing? Ring. I mean, like in can you? You can? How do you do that?
You have an intermediate task, and you pass, like, that's always like, what's the word, responsive?
I have an intermediate task, which is always listening.
So you can, like, synchronously send a message to the middle.
Yeah.
And the other one can synchronously, like, retrieve it. And
Yeah, you lost me there. Because, okay, I'm the task in the middle. I have my ear open on the sending side, on the receiving side. So the sender can actually stuff something into my ear anytime. Is this ear still open when I'm sending? Really? Well, I probably also need to implement a buffer, because asynchronous message parsing is usually defined by you have a certain number of messages which is stored there. That's not the issue. The issue is while I'm waiting for the receiver to talk to me, can I at the same time listen to the next message which is coming in? No, you don't have select statements which are mixing ingoing and outgoing, incoming and outgoing. They don't exist. For good reason they don't exist. So you have two tasks. Ha! Solution. I have two tasks. Like that, right? You have one task which is always listening, and one task which is always willing to send. How did these two tasks communicate? Shared memory. Can they block on this shared memory? Shit. So if they can block on this shared memory,
You can approximate.
it's kind of working. What does this tell you in general about asynchronous message passing? Be careful about the assumption that asynchronous message passing is really, really fully and all times asynchronous. Asynchronous message passing can also, most of the time, block you for just a little bit. Because exactly that is what happens behind the scenes. This is how asynchronous message passing is actually implemented and need to be implemented. Because you only have active entities someplace. And they have to have some synchronization mechanism on shared memory at some point, or on a shared task. So you do have still synchronization points. Asynchronous message passing does not mean you have no synchronization points left.
But you can guarantee that the whole thing's going to happen really quickly, right?
Yeah, are we happy in the real-time community with it's happening really quickly?
Well, we know it's going to happen in some time. There's no that's quite conveniently small.
Yeah.
The alternative, if you were somehow to directly do asynchronous or do some other method, it's still going to take some amount of time.
Yeah.
It doesn't matter what's going on the inside of the top user perspective.
Yeah.
You know it's going to happen within some time, and it's quite small.
That's fine. Yeah.
What if you've got like 1,000 tasks trying to send messages?
So it depends also on the usage of this whole thing. How many tasks are hammering on that asynchronous interface at the same time?
Or you can split the middle task
To 4 tasks, and then
two compartments. No item standing in the middle was stand by each the receiver and the sender. So receiver and sender, each of them has a for standby task.
so I have 4 tasks then.
Well, you have 4 tasks, yes.
You can do a lot of cell splicing here, one after the other. At some point, you need to make them communicate. And that means you need to synchronize at some point between these 2 tasks. The moment you do that, They will not be 100% responsive, but responsive in a certain window. So if predictability is good enough in terms of upper bounds, and you're possibly even willing to spin inside of these tasks, because sometimes you need to also guarantee that you're spinning around in there. You have some busy waiting loop to guarantee that. Then you can do that. But a fully asynchronous message passing interface in that sense, could you physically do that? If you have full control over your system, could you build a system for me which has asynchronous message passing, seriously asynchronous? Could you physically do that? You could?
Yeah, so the project object becomes kind of a queue that's not really blocking. So it has this retrieving the message at the end and converting the message into the queue and
And when the queue is empty?
well, then you have no messages anyway.
No, what happens with the very first message? That only works if you have always a few messages already in the buffer. But if the buffer runs full or empty, you have two extreme cases where your method falls flat. Couldn't I define a buffer which is actually fully asynchronous? Okay, you have two active tasks. You want to make sure that this task can send messages in this direction without ever being blocked. And you want to make sure that this task can receive those messages without ever being blocked. Is that physically possible?
Circular buffer.
Circular buffer has the same corner case issues.
Would something like the double clock memory work?
Something like what?
The double state memory.
The double dual ported memory?
Yeah.
Yeah. So you have a double clocked entity in the middle, which is able to, in one clock cycle of each of these guys out there, do a read and a write. And that's actually the physical solution for that one. If you have the middle part double as fast as the outside components, you have a chance of emulating completely block-free simulation, because this guy is blocking so quickly and unblocking so quickly that the outside task cannot observe that block. It is still protected in terms of the integrity of the data structure in between, but it's switching so quickly that the outside task is not noticing that. That's your chance. If you use what? I don't understand.
If that part of memory is full.
It's full. Yeah, well, you always, in those kind of real-time communications, you're not worrying about full memory ever. I'm not saying that doesn't exist, but what happens if the memory is full in a real-time system? What do? You dump the old data. You ignore the old data. You override it straight out. You don't care about the old data at all. In a real-time system, you're only interested in the most recent reading. You're not interested in a history lesson. You don't want to read data which has been pumped into that queue 20 years ago. You want to have the most recent pieces of information. That could be possibly the 5 most recent pieces of information. But if somebody has written 6 pieces of data into this buffer, you automatically, always, in a hard real-time system, throw away the last one. Or you don't explicitly delete it, you just override it directly. So if you have a circular buffer, for example, in there, you have an overriding without any kind of checking whether this has been read or not. You don't care. Yeah?
But if it's double clock,
Yeah.
can it ever be filled? Because if you're going twice as fast as the other guys,
Yeah.
they can't possibly send stuff fast enough when you are sending the receiver, right? Or
The outside tasks have to be slower, yeah?
yeah, so how can you be full? Because then I'm receiving from this guy something to that guy twice as fast.
Yeah.
Then he can actually send to you. So you can never be full.
The fact that you are writing here at that speed doesn't mean that the other task is ever reading at all. So what do you do if you only have a task which is constantly writing into this dual-ported memory? without anybody taking this data ever out. Then this data will automatically be overwritten in there, possibly in a cyclic way. But in the most extreme case, maybe you only store the last piece of data. Maybe you only make sure that you have a multi-buffer environment which only guarantees that data will never be, the integrity of this data will never be violated. So you cannot mess with data which is currently in the buffer, but you can switch between multiple buffers. One is for reading, one is for writing. In fact, in the end, you will need 3 buffers for that, because you will have, for example, one buffer which is currently read from the receiver side. And if the sender is many, many times faster, the sender still needs 2 more buffers to alternatively write into the buffers on the dual-ported RAM side. And then the moment that the receiver wants to receive something, it will check out the buffer which is currently not being read, and then the sender can keep alternating between the other 2 buffers. So by bare minimum, you will need 3 buffers to do that trick. Then you can guarantee data communication without any blocking interference at all, if you have the hardware to support that, which you have seen in the time processing units on the PowerPC architecture. They have exactly that. But it's not classical stuff you find in your desktop environment, obviously. Okay. There you will always have some form of blocking operation in the game. Cool. Emulating a number of different things. From a logical perspective, you always have synchronous message passing as the logical foundation. If you verify systems, people prefer synchronous message passing. It's way easier to handle from a verification perspective. Address space, symmetrical addressing, directly versus indirect addressing. You probably remember these things. Most systems use asymmetrical addressing, which sounds weird, but it's much more common. Asymmetrical addressing means that you are putting an address to the parcel which you send. You're only sending to one specific server. But the server doesn't have the symmetrical thing on the receiving side. The server can receive from many different entities, not only from one. If you have a symmetrical addressing mode, that's often referred to as channels. Channels have only one sender and one receiver, and then you don't need to address anything beyond that point anymore, because you open a channel between these 2 entities. This is message passing, which is completely symmetrical. You can then also exchange messages in both directions. Many-to-many, one-to-one. This is not that spectacular. Message structure is more interesting. This is a very pragmatic thing. The structure of your messages. Can you send types in messages? If you have an object of a certain format, of a certain structure, can you send this as a parameter in a message? Yes. To a computer which has little endian when you're sitting on a big endian machine? Yes. Can you? Do you now have to start looking worried? Do you have to ask questions? Do you have to start implementing things? Is this all automatic? Does this all happen for you?
Well, you always need to define protocols. Otherwise, you're just blindly sending bits and anyone can interpret anything. If you've got the protocols, you have enough to tell them how to understand more things, and you can just go from there and tell them you want.
Yeah, but very pragmatically for you as a programmer, if you sit there with your compiler and you want to send a message to somebody else on a different computer, do you have to now look up this protocol? Do you have to encode your data structures by actually writing code to encode those data structures, fitting this protocol and this data format there? There are lots of systems which are smart enough to do that for us. The answer is this point has changed over the last decade drastically, because 10 years ago, many of us have been wasting years of programmer time doing just that. You needed to send messages, simple things from one process to another one, to one C machine to another C machine, and what you have been doing is you have been marshalling your data structures by hand into a bunch of bytes. And then you could send these bytes off, and on the other side, you wrote the same piece of code to take these bytes and put them into memory in a certain order again that you can actually make heads or tails out of them. Unfortunately, this is pretty much history, and I don't think there is any semi-self-respecting language left which leaves you on that one. Whether it's automatic enough to do the full encryption, marshalling, byte swapping, if you have little endian, big endian machines on both sides, that may be a bit of an advanced topic, and not all of them will do that for you, but to be able to serialize your data in a somewhat defined way, yet you can even read this from another programming language, for example, not only from the same programming language, that should be going completely automatic today. That's one philosophy of doing that. Do you know any system which does that? Okay. That's usually called a middleware, where you have a layer in between the network and your applications, which can exchange and marshal information, but they need a description. So in this middleware, you usually leave a description what the object structure looks like in a language-independent format and way, and then the marshalling is done by this middleware based on this description which you deliver there. This has not been that successful because that's an extremely clunky operation. The semi-automatic way of describing your data structure. This is classically CORBA. CORBA was very dominant 5-6 years ago as a middleware, but I don't think many people are using it today anymore. Have you ever used CORBA in your life? It was classical data marshalling, language and platform independent middleware to exchange messages between multiple systems. But it's a monster. And it grew larger and larger until people lost interest in that monster. I think the only conversion left where you have to do it manually is POSIX and C. These days, everything else should be automatically generated for you. And so communicating between any high-level language these days is fairly easy. And as the formats are also mostly defined by the CPU architecture, so as long as you stay on the same CPU architecture, your data structures can be easily exchanged. Cool. So much for message formatting. We don't have to do that manually these days. If you ever need to do that manually, or if you have to touch that system by hand, that's the streams interface in Ada. Same thing as the serialization interfaces in other programming languages, where you can just take a data structure and call some serialization method on this data structure, which just rolls it out into a byte stream. And that's the same thing with the Ada streams, where you can obviously, this is all implementation dependent because it has to work over multiple platforms. But for all of your data types, you have these attributes defined: read, write, class read, output, input. And what they're doing is you can do this on flat data types, on object-oriented data types, meaning you have a few more attributes which are being marshaled into that one if it's an object-oriented data type, or you can have the bounds, discriminants, or subtype information as part of this whole thing as well. And if you need to do that like that, then you have full control over the whole thing. Classical example, you want to send, for example, an array from one computer to another computer someplace, and you know the size of the array already because it's a constant on both sides. You don't need to put the array boundaries into that data type every time you actually send that message. And here you have control over that. You can put these boundaries in there, or you can leave them out. Right. Just a handful of examples for message passing interfaces. What do you usually get on offer there? Ordered, all of these message passing interfaces only offer ordered message passing. Can you imagine a case where you have not ordered message passing? Have you ever seen unordered message passing? Yes, you have. Plenty of it. Yeah, the internet is based on it. So whatever happens in terms of low-level message passing on the internet itself, these packages can be spread out over many different routes, and they can actually overtake each other. That's a very basic idea of IP. And you have a higher level protocol which then sorts them into the right order on the other side. But on a lower level message passing perspective on that thing, this message passing interface is explicitly unordered. You send out UDP packages and you have no guarantee in which order they arrive. Right? But these interfaces are all ordered. Most offer asymmetrical and symmetrical. Ada does not offer symmetrical message passing. There is no concept of channels in Ada like you would have in Go, for example, where you have only this concept of channels and nothing else. I should put Go into that one because it actually has a quite widespread and understood system about message passing these days. Synchronous and asynchronous. POSIX does not offer synchronous message passing, it's only asynchronous. Most other systems use both. Now you will ask, why is Ada offering asynchronous message passing? It becomes asynchronous the moment you actually go onto another platform. If you do remote procedure calls, they can be labeled as asynchronous in Ada. And the contents itself, hopefully, is fully marshaled, fully automatically for you. So you can write fully typed here, you don't care. Whatever you define as a data type, you can use as a parameter for message passing. Why would you be restricting yourself there? I hope this should be standard for most languages these days. Chile is a very old language, and they were not quite that happy to marshal everything. They only marshaled very basic data types. Okay, and just as a reminder, Java does not have any message passing system defined on it at all. Coming back to one of my favorite programming languages, how does message passing look like in OCaml? And you have a whole multitasking message passing example again in a few lines. OCaml is beautifully compact with everything it does. It's like Python indentation based, and you can have everything parallel or sequential. You decide this on a statement by statement basis. Those 5 statements are parallel, those 5 statements are sequential. In this case here, you have those 4 instances parallel, and you have the loops, the for loops, in this case sequential. And so I already have 2 tasks. One is sending, one is receiving. The sending is done with the exclamation mark, the receiving with the question mark. Pretty sparse notation. And these 2 entities will automatically be synchronized because all message passing in OCaml is synchronous message passing. And this is as easy as you can formulate synchronous message passing in a more logic-oriented and cleanly defined language like OCaml. Yeah, this was just for entertainment. This is all the OCaml 2 keywords which we will ever need. And actually, they are pretty much all OCaml 2 keywords. And that describes the full language. And it's a concurrent, distributed, and real-time programming language just with these handful of keywords here, which is quite beautiful compared to learning the 1200 fine print pages of the Ada reference manual. Learning those handful of statements here as a full language description in distributed real-time programming is quite nice. Chill has both, and I think I like the naming of that one, is very clever. Asynchronous message passing is defined by defining a buffer, and synchronous message passing is defined by defining a so-called signal, not to be confused with POSIX signals. To imply that asynchronous message passing is always leaving something in the buffer and reading something out of a buffer, you have to define the size of the buffer if you want to be having a useful asynchronous message passing. So if you want to have a useful asynchronous message passing system, while synchronous message passing is about synchronizing, signaling in that sense, between two tasks. Otherwise, they're looking syntactically almost identical. Besides that, synchronous message passing has to be slightly differently addressed. And depending on the channel type, this automatically becomes then asynchronous or synchronous. And of course, Ada has message passing, as you already have been using plenty. There's nothing spectacular there. Now, message passing in Ada is a little bit more liberal as opposed to protected object entries. You can have blocking operations in those except statements. They can also be nested. Why is Ada so much more liberal on the message passing side here? Do you have any logical explanation for that? Why can you block inside one of these entries? What could be a rationale for that? If you look at memory-based synchronization, the assumption is that those protected objects would never go to sleep or go away. They will always be there to process little bits of pieces for each of those tasks. They're all going, next one comes, going, next one comes, going. But they're always available minus the number of tasks which are storming into that one, or modular the number of tasks which are storming at it at the moment. But each of these tasks will only get a small slice because they cannot block in there. They can only run a very predictable small amount of code in there, and then they leave. Message passing is by its very definition different. Message passing, you buy into the very concept that you could wait for a long time. Why? The other task may never be listening to you. It's very different from protected object, which is by definition, unless somebody is currently briefly in there, it will be available again. It's a passive object which everybody can hammer on. Message passing requires that the receiver is not doing anything else at the moment and actually listening to you. And this is completely undefined how long that takes, or if the receiver will ever be listening to on those channels. So message passing, by its very definition, is an infinitely blocking operation from the perspective of planning it from the sender side. So it doesn't matter whether you have also the possibility to block this task after you accepted it. The sender already bought into the concept logically that this is a potentially very long blocking operation. Yeah, obviously there cannot be direct access parameters, count attributes exist, entry families exist, private entries exist, requeue works, all of that is there. Okay, that was the fast forward version for the advanced guys about synchronous operations. Any further questions about synchronization primitives in terms of memory and in terms of message passing from your current perspective? How is message passing implemented? How is message passing implemented? That depends very much on the scheduling environment. So message passing, I mean, your question is probably targeting, is message passing not just a camouflaged memory-based synchronization method? It's not. Message passing will suspend a task waiting for a certain predicate to come up, which is triggered by the receiving task. So the scheduler has explicit knowledge about these communication attempts and can make tasks wait exactly until the receiving task will pick up the call on the other side without any memory-based synchronization in the meantime. So message passing has to usually go through the scheduler to do that, to synchronize these multiple tasks. It does not have to go through memory-based synchronization. Does that answer your question? Right.
You are trying to message passing with some task on the other computer. It's not
Then often synchronous message passing will be broken at some point into asynchronous message passing. That's a problem from a real-time perspective. Because what you want to have from a real-time perspective is clean synchronous message passing. But if you have some IP link in between, this is physically not happening. Is it even possible to have synchronous message passing between physically separate computers? Is that even possible? Well, you always wire them up somehow. It's called a network. But can you wire them up in a way that you can actually have synchronous message passing between them? Do you need to emulate it? Can you actually physically implement it? You seem to be worrying about this. What would stop you from implementing it physically? Well, what do you need to have actual physical synchronous message passing between computers which are 10 meters apart? What do you need to do that? Actual hardware synchronization wires. You need to have more wires than just the one cable where everybody can just pull a signal down and write in a collision-oriented style from multiple ends. This cannot be a non-deterministic collision-oriented protocol. This has to be a strict handshaking protocol where you actually say that you want to receive data, which comes on a special line to the other computer, and the other computer can then send data to that one. Clean handshaking between those computers. That needs more hardware. You need more wires to do that. Is that being done? Sure, it's done. You have real-time buses, real-time communication systems, which just do exactly that. You need to have an explicit arbitration process or synchronization process between these nodes, but this can be done, and it's done. It's just not your classical Ethernet port which does that. Even though that changes, because your classical Ethernet protocol is no longer collision-oriented. Right? You still have learned in your early years that Ethernet is a collision-oriented protocol, right? Is it in your system? How many computers do you have wired up on one cable in your current Ethernet system? Exactly 2. If you have only exactly 2, and moreover, You have dedicated wires in both directions. Where's the collision? There isn't any. How is that resolved? How can I actually how could I have possibly made this migration into a collision-oriented protocol into a point-to-point collision-free protocol? Yeah, we moved this all up on the level of network switches today, so everything is a routing problem these days. So you moved it up from the level of the hardware layer, which is collision-free today, to a logical level where you resolve the collisions on a logical level called a network router, or a switch in that case. Okay. So yes, sure, it can be done. Can you hard synchronize computers? Is that a possibility? That you have them even synchronizing their clocks, their pulse signal, their communication path? Can you do that? Yeah, the assignment does that. Kind of, yeah. So it's not an easy problem. If you have enough locality that your devices are only a few meters apart, you still can consider to bite the bullet of having explicit synchronization wires which are synchronizing all of your devices explicitly. This is also done in real-time systems. So you have explicit bus systems which are hard synchronizing and your clocks in your different system. But it doesn't scale because speed of light doesn't change from that. And if you have your systems in a network or wider apart from that, you need people which have been doing this assignment to solve that problem. That's perfectly correct. So that ends synchronization. And we will enter a completely new world on Friday and go into real-time scheduling.